This is video 15 of the GCSE Physics video series all about electromagnetism. Parts of this video are going to be for double scientists and physics GCSE students. Some of this video is just going to be for physics GCSE students. I'll see if I can remember to point out which is which. So, starting with magnetic fields. Now, magnetic fields are usually introduced at primary school, maybe year 3, year 4, something like that. So you probably have some familiarity with magnetic fields already. So a very convenient way of young children experiencing or investigating non-contact forces. So we've got some technical words here to define, a lot of technical words that we need to be able to use. The first is magnetic field. So any field, a force field, is a region where a force is felt by something. So a gravitational field is a region where a gravitational force is felt by masses. An electric field is a region where an electric force is felt by charges. And a magnetic field is a region where a magnetic force is felt by magnetic poles. We'll come to poles in a minute. Some metals are what we call magnetic metals. Actually, it's more complicated. It's always more complicated than that. Ferromagnetic metals, doesn't matter. Some metals are magnetic, which means that they can become magnetized when they are in a magnetic field. So, a magnetic metal. You need to learn iron, cobalt, and nickel. Steel contains iron. Most steel is magnetic. You can get phases of steel that aren't, but most steel is magnetic because it contains iron. So iron, cobalt, and nickel are your magnetic metals. Those metals, when placed in a magnetic field, they become magnets themselves. When you remove them from the magnetic field, they stop being magnets. So because they become magnets, we say they have induced magnetism. Magnetic metal placed in a magnetic field produces its own magnetic field, reinforcing the magnetic field in which the metal has been placed. So we say that we have induced magnetism. We did mention poles, so I'll skip field lines for a second. We did mention poles. Magnetic poles are points on magnets where the field lines are, where the magnetic field is most strong, where the magnet is strongest, if you like. So there are north poles and south poles of magnets. That's the terminology we use. We don't talk about positive and negative. We do talk about north and south. If you were to take a magnet and you were to investigate it, look at it closely, there is a north pole and a south pole of a magnet. If you were to cut it in half, you would now have two magnets, each with its own north and south pole. It is not possible to have an isolated north pole. It is not possible to have an isolated south pole. Now, I know there is research ongoing to try to find magnetic monopoles, but they are part of a very different framework of physics and not the classical physics that I'm using to introduce the idea of magnets to you here. So don't worry about those. That is some very cutting edge, very frontier physics, certainly beyond A level even. So magnetic poles always come in pairs. Now this is very different to the electric charge, where you can have an isolated positive charge and you can have an isolated negative charge. They don't always have to come together. And very different to mass, where there is only one flavour of mass. You know, there are two flavours of charge, positive and negative. There's only one flavour of mass. Well, here, magnetic poles have two flavours, north and south, but you can't separate them. Well, you can separate them, but you can't isolate one of them, because it will always have a south pole somewhere attached to it. So that is about poles. And it turns out that around the poles is where the magnetic force felt by something which can be magnetized is strongest. Now, field lines. These are a way of visualizing the direction of the magnetic force that is felt by the north pole of a magnet when placed in the field at that point. The south pole of a magnet feels a force in the opposite direction to the field lines. So if I look at this picture here, we've managed to visualize the field lines by taking a bar magnet and sprinkling iron filings around it. The iron filings, iron being a magnetic metal, the iron filings become magnetized. There's induced magnetism in the iron. So each iron fleck, each little piece of iron filing, has a north and south pole. South poles attract north poles. North poles attract south poles. Like poles repel, unlike poles attract. And so what the iron filings will do is line up, where the south pole of one iron filing will attract it to the north pole of the nearby iron filing. And the opposite side of that is the south pole of that iron filing, which will connect to the north pole of the next iron filing, and so on. So the iron filings will line up, and they will show you, they will allow you to visualize the field pattern. Now, they won't tell you the direction of the field. The field is going away from the north pole, but towards the south pole. Oops, shouldn't have drawn the arrow part on that. Now I'm going to have to do it for all of them. No, I've messed it up. Let's clear it and try again. Let's just draw a field line emerging from here, trying to follow the general curvature. Let's try and follow the general curvature of these lines. Maybe I could do some coming out of the end like this, and some coming out of the end like this. I think I've done an okay job of that. So the field lines emerge from the north pole, and they go into a south pole. Now remember, these field lines are not really there in a sense. There's nothing tangible to them. You can only determine that there are field lines there by placing something in the field that experiences that force. The force is real. The field is there, but the field lines are something that we use as a diagram to visualize the direction of the field in that region. So the magnetic field in this region is pointing up. The magnetic field in this region, don't know if you can see my cursor clearly enough, the magnetic field in this region is pointing down. The magnetic field in this region is pointing up. The magnetic field in this region is pointing down. In this region it's pointing from left to right. And in this region it's pointing from left to right. They are the directions of the magnetic fields. And so the magnetic fields emerge from north poles and go into south poles. If I were to place the north pole of a magnet here, it feels a force in the same direction as the field lines, so we have repulsion. If I were to place a south pole here, it feels a force in the opposite direction to the field lines, so we get attraction. If I were to place a north pole here, it feels a force in the same direction as the field lines, so we get attraction. If I were to place a south pole here, it feels a force in the opposite direction to the field lines, so we get repulsion. So that is how we can understand attraction and repulsion in terms of fields, the direction of the fields, and the poles placed in the fields at those points. In order to actually determine the direction of the field, we'd need to know which side of the magnet is a north and south. In order to do that, we need another magnet on which we know which side is north and south. So here we can see I've coloured the red side as the north pole side and the blue one as the south pole side. And these little plotting compasses, the tip of the plotting compass is a north pole. The tip of the plotting compass. You can see they form an arrow. So the tip of these compasses is the north pole. I'm just drawing all the little ends to indicate all these little north poles. And the compasses have rotated themselves around so that the north poles point towards the south pole of the big magnet in the middle, and the north poles of these plotting compasses point away from the north pole of the magnet in the middle. I can't even see that one. Oh, there it is. See the reflection from that bit there. So that is what we see. So if we use our plotting compasses, where we know what the north pole is on the plotting compass because we've shaped the needle that way, then we can determine which side of the bar magnet is a north pole and which side is a south pole. And if we move the plotting compasses around, we can use that and connect the directions of the plotting compasses to create the diagram above. It's a very common practical that students will do. Of course, that does beg the question, how do we know which side of the plotting compasses was the north side and the south side? Well, that's no problem. The needle that we call north was pointing towards the Earth's north pole. The Earth's north pole, what we mean there is the Earth's geometric north pole. And the south pole of the little plotting compass points towards the Earth's geometric south pole. Now, if you do Duke of Edinburgh Award, or if you're in the Scouts or something like that, so that you do any sort of map reading and compass work with orienteering, then you will know that you need to correct the angle your compass says for true north. There's geometric north, true north, and there's magnetic north, which is a few degrees off. And it changes, and I don't know what it is at the moment. It's certainly different to what it was 25 years, 30 years ago when I was a Scout. So it's definitely changed, because the Earth's magnetic poles move around. Very slowly, but they do move around. So in D of E, orienteering, Scouts, something like that, cadets, you will have learned that there's a geometric north, a true north, and a magnetic north, which is slightly off. The issue is what they call the magnetic north pole in those subjects, in geography, in geology, in map reading for Duke of Edinburgh, what they call a magnetic north is in fact a magnetic south pole, because it is the side which is attracting the north pole of our plotting compass. It's just a quirk of how we first came to define these terms. We had a material called lodestone, which was discovered in China thousands of years ago. This lodestone, which was an iron ore, where the iron cooled slowly in the Earth's crust. If you suspended it from a long, thin piece of string, it would always rotate around and point the same way. So the side that pointed towards the north, we called the north-seeking pole. And the side that pointed towards the south we called the south-seeking pole. It's quite a mouthful, so over time that just became the North Pole and the South Pole. But of course, in order for the North Pole of our lodestone to be attracted towards the geometric north, it means the geometric north has to be the location where the field lines are going into the Earth, which is the magnetic South Pole. But don't worry, soon enough the poles will flip and all of this video will be out of date. So I should say that this is correct as of recording in August, I don't know what the date is, 23rd of August 2024. By the time you watch this, it could be different. You never know. The process of making a magnetic metal have its own magnetic field, placing it in a magnetic field to make it have induced magnetism, we call that magnetization. Making something a magnet is magnetization. And you can have very temporary magnetization, as is the case with iron, cobalt, nickel. Or you can take something like iron, you can dope it with rare earth elements, heavy elements, and change it so that when we induce a magnetic field in that material, it magnetizes more permanently. It's what we call a hard magnetic material rather than a soft magnetic material. But a hard magnetic material, when it's got its magnetic field, when it's become a magnet, it stays a magnet for a much longer amount of time. So your permanent magnets, like what you might use on a fridge to keep your music certificates stuck on your fridge, or I don't know what you do, those sorts of things, they are hard magnetic materials. Whereas in a magnetic hard drive, the magnetic disk in a hard drive, I don't know whether anyone still uses them anymore. Solid state drives have become the norm, but you could probably still get old magnetic storage. Those who want to use something which is magnetically softer so that you can change the direction of the magnetic poles on the small elements within the disk to set the bit to be 1 or 0. You don't want it to be too soft a magnet though, because otherwise, as soon as you've set that bit, the magnetic right head moves away from the disc, and then the bit flips all over the place anyway. So you want it not too hard, not too soft as a magnetic material. Just any old iron, that is a very soft magnetic material. Right, so that's the reintroduction to magnetic fields. Probably did something about that in primary school, but maybe not in that sort of detail. Let's move on to lesson 90. Lesson 90 is about magnetic fields of electric currents. Yes, it was discovered by 𝗟𝗏𝘀𝘀𝘀 many, many years ago that if you had a current passing through a wire, then around it there is a magnetic field. Now, unlike with permanent magnets or induced magnets where we've taken iron and placed it in a magnetic field and so on, these magnetic fields, you can't really describe a north or south pole for them. Magnetic field lines are different, very, very different to electric fields and gravitational fields. With electric fields and gravitational fields, they extend to infinity in all directions. The field lines start at a point which is the charge for electric fields, or the mass for gravitational fields, and then extend out to infinity. With magnetic fields, they don't work that way. The field lines form a closed loop. And 𝗟𝗏𝘀𝘀𝘀 identified that these, I mean, we haven't drawn the whole loop here, but there is a certain, this should continue. Let's try and get my pen. That should continue round in closed circles like this. He discovered that there were these circular magnetic fields around current-carrying wires. There's no North Pole, no South Pole, because there's no point from which the fields are emerging or to which the fields are receding or going. So if I place a piece of iron in this field, it will become magnetized to reinforce this field by producing or having an inducing magnetic poles in the piece of iron that are orientated in this way. The North Pole being the point the field is coming out, the South Pole being the point where the field is going in to reinforce that field. So now we have a North Pole and a South Pole. But if the iron was not there, if we didn't have the iron, then we wouldn't have any way of describing a North Pole or a South Pole. It just wouldn't make any physical sense to call them that. So that is the pattern of fields around a current-carrying wire. Now that's interesting. If I have a current in a wire, it has its own magnetic field. We'll come on to why that's so interesting in a little bit later. There is a direction to that magnetic field in relation to the current, and you can work out the direction by using your right hand. If you do not have a right hand, then my apologies, but this is the standard way of working it out. If you were an owner of only a left hand and no right hand, you would have to use your other hand and reverse everything. If you don't have either hand, then I'm afraid you're going to have to visualize what it would look like if you did. This is my right hand. If I curl my fingers, I can curl them in that direction. I can't curl my fingers in the other direction. It's just not possible. Might be able to do it a little bit, but I can't curl them all the way around in that other direction. If I did, I'd probably end up breaking the bones in my hand or something. So I can curl my fingers quite comfortably in one direction. If I had a current-carrying wire as a vertical wire here in front of me, and I gripped it with my hand such that my thumb was pointing in the direction of the current, then my fingers wrapped around the outside of that current-carrying wire would indicate the direction of the magnetic field. It's called the right-hand grip rule, or sometimes the right-hand screw rule. The right-hand grip rule, indicating the direction of the magnetic field. So if you look here, here's my thumb indicating the direction of my current. My fingers curl so that in front they're going up and to the left. In front they're going up and to the left. In front they're going up and to the left. That is how that works. The further you are from the wire, the weaker the field is. And we indicate a weaker field by drawing field lines farther apart. That's the same with electric fields, and the same with gravitational fields. The farther away you are, the weaker the field is, so the farther apart the field lines are. Well, these fields form closed circles, so it's a little bit more complicated, but you just draw the circles with increasing radii the further away you are from the wire. When we say current, we are talking about conventional current. In a wire, if there is a current in the direction indicated by the I, then electrons are flowing in the other direction. Yes, we know that. We're not interested in electron flow, not at the moment. We're only looking at the direction of the current. We are defining current as the direction at the rate of flow of positive charge from a positive potential to a less positive potential in a direction where the potential decreases. So that is no positive charges actually moving this direction, but we can talk about the effective flow of positive charge, which is the opposite direction to the flow of negative charges. There are no positive electrons. So that is with a simple length of wire. What if I were to coil that wire up? Well, if I were to coil that wire up, and you can test this yourself, and when I do this in the classroom, I get pieces of wire in different directions, and I construct this bit by bit. I don't want this video being too long, longer than it needs to be. If you do that, then you will find that you end up with a field pattern that is the same as you get for a bar magnet. Okay, if I look at any point here, let's just look at this point here where my cursor dot is. I don't know if you can see my cursor dot. Maybe I should switch it to a... No, it's doing that thing again where it doesn't let me click. Maybe I can get something like a laser pointer if I go like that. Laser pointer, there we are. You can see that dot more clearly. So if I place my dot here, the current is going up. So I can take my thumb and point it up. The fingers are going into the middle of the coil. That's the direction of the field. And outside, they'd be going in the opposite direction, which is what we can see here and here. If I take the wire at the top here, the current is going away from me into the board, which I suppose is that way from your perspective. And so if I rotate my fingers, do it with me. Get your hand and do it with me. They go into the middle of that coil, and on the outside of the coil, they'll be pointing from left to right. Inside the coil, they'll be pointing from right to left. And I could do that for the bottom of the coil as well. The current's coming towards me. The magnetic field, the blue arrows, are going into the coil from right to left, and on the outside of the coil they're going from left to right, and I could do the bit in the back as well, and I can convince myself that this is the shape of the magnetic field, because it is. There are all sorts of other mnemonics that you can use, like for example considering looking down each end of the coil at the current, and there's S's and N's to work out which side of the coil is a north or south pole. I really don't like those mnemonics. I don't know why, so I've not included them here, but you can find them easily enough. So this end, over here on the left, is the north pole of this coil of wire. And this end over here, on the right, is a south pole of this end of the wire. When we take a wire and we coil it up, and we intend to pass a current through it, there's a special name for that. It's called a solenoid. Solenoid, coil of wire, we can pass a current through it. Now, when we pass a current through a solenoid, it gains a magnetic field. There's an induced magnetism induced by the current, and we call it now an electromagnet. A solenoid with a current passing through it. It acts like a bar magnet. But unlike a permanent magnet, I can switch this one off just by switching the current off. And if I switch the current off, no current flows, magnetic field disappears. And I can make the electromagnet stronger by having more current, and I can make it stronger by having more turns. Each of these turns adds more field lines. Each time you add an extra turn, you add more field lines, making the field stronger. So I can add more turns. But I can also place something like iron, soft iron, so I can easily turn the magnetic field off again afterwards. But I could place something like iron inside this coil, and what the iron will do is become magnetized as well, with its own magnetic field reinforcing the magnetic field that induced the magnetization in the iron. So putting an iron core in a solenoid has a massive effect on the strength of this electromagnet. This diagram here is just the same picture as the one on the left, in the one in the middle, except I've done a cross section. And I've shown this because I want to show a convention. When we have anything coming out, we're working in 3D now, aren't we? We're struggling here because we're trying to draw diagrams in 3 dimensions. So when we're drawing a 3-dimensional diagram, anything where we indicate a direction to the left, we can just draw an arrow pointing to the This is reflected, an arrow pointing to the left. If you want to draw something pointing to the right, you just draw an arrow pointing to the right. Up is up, down is down. What about forward and backwards? How do we do that? Well, if we want to do forwards, indicating something coming towards us, we use a dot. A dot is an arrow pointing towards us. Now, if we want something pointing away from us, we use a cross. So think about it like an arrow, like you were, an archery arrow that you were firing. If the archery arrow is going towards you, you're going to see a small dot. If the archery arrow is coming away from you, you can see the cross from the flight. Okay, it won't be a cross. It'll probably be sort of 3 bits on it and all the rest of it. But okay, you get the idea. The circle's just because there's a wire. This is a coil of wire going around, and we've taken a slice, a cross-section of it. You don't need the circles, but the crosses indicate something going into the page, and the dots indicate something going out of the page. And in this diagram, that something is the current. This is current going in, current coming out. And you can take your right-hand rule, your right-hand grip rule, and you can say when the current is coming out towards me, magnetic field goes like that, which is exactly what this diagram shows. And you could do the same thing for the current going in. Magnetic field goes like that, which is exactly what this diagram shows. Magnetic field in the middle of a solenoid is pretty much uniform. Why do we say that? We say because the lines are all about the same space apart and because they're all pointing in the same direction. So that's how we define a uniform field. The field strength is the same at all points inside that coil. Pretty much. I think that's everything I need to talk about in terms of electromagnets, making a magnet using a solenoid. Lesson 91 starts looking at the uses of electromagnets in devices. So all of these applications use the same very, very simple principle, which is I have an electromagnet I can turn on by having a current, turn it off by not having a current. The simplest example of that is a scrapyard crane. Big electromagnet at the bottom. If I want to pick up iron or magnetic metals, maybe some steel, so I can sort and separate the metals and leave things like aluminium and copper behind, what I can do is I can use this massive electromagnet, shred up all the metal, turn it on, put it in the metal, take it out again. What sticks is magnetic. Then move it, turn the magnet off, metal falls. So that is the most basic use. We've also got electric bells. The electric bell, I'm going to draw on this electric bell because I think that might help us visualize what's going on. So let's get the pen out. In this first example, we've got a power supply. If we shut the switch, current is going to go from the positive side of the battery. It's going to go up here, and then it's going to go through the solenoid, blah, 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 which means that that solenoid is now turned into an electromagnet. This current passes through here, through the switch, and then back to the supply. So when the switch is closed, switch K is closed, current passes through this circuit, which means the electromagnet is switched on, and part A is an iron, a soft iron armature. It's just a soft iron arm called an armature, which is now attracted to the electromagnet. So this is attracted down. The beta hits the gong. It makes a bing noise. But as the A is attracted towards E, that we end up with this picture on the bottom. This contact switch S, which was in contact, now isn't. So now there isn't a route. You know, if we follow this route, the current goes la 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 la, and now it can't get to S. There's a broken circuit. So the current switches off. Well, if the current switches off, then E is no longer an electromagnet. And if E is no longer an electromagnet, it's no longer attracting A. So if we put this iron armature on a spring, then the armature is going to be pulled back again. So it's going to leave the gong B, and we're going to make contact at the contact switch S again, which means we're going to have a current again, which means A is attracted to E, which means H strikes B. But when that happens, contact switch S breaks, so the current switches off, so A is no longer attracted to E, So H leaves B, gets pulled back again, which makes the contract switch S, and so on and so on and so on and so on and so on. So we cycle between between picture 1 2 1 2 1 2 1 2 1 2. Every time the gong hits the bell, it makes a bing noise, and hits the bell often enough, we hear that as a ringing. So that's how an electric bell works. A relay. So a relay is a way of controlling a very high power circuit, switching it on and off, using a very low power circuit. It's very commonly found in things like cars, or I worked at McDonald's for many years. The McDonald's grill, the heating element in the McDonald's grill is a very high power heating element. It's going to hold those grill platens at 177 degrees Celsius at the bottom and 218 degrees Celsius at the top. And they're open to the air, so you have to constantly be heating those platens. It uses a three-phase power supply. It's huge grills. So there must be some way of switching off the grill platen when the temperature reaches the right amount and switching it back on again when the temperature drops to maintain the temperature of the grill platen. So there are sensors, and those sensors feed information to what they called a computer, which would decide whether to switch on or off the grill platen to maintain that temperature of 177 on the bottom, 218 on the top. Well, that's fine. The problem is, if I've got, let's say, I mean, it's three-phase, so it's more like 400 and something volts, but let's say I've got 230 volts. Let's keep it simple. So I've got 230 volts across the heating element in my grill. I can't put 230 volts across the computer because it will just blow up. All the electronic components will explode. And I do mean literally explode. The capacitors will make a bang and blue smoke will come out. So we can't do that. So what do we do instead? Well, we can use a relay. So the computer operates on about 5 volts. If you've ever built a computer, you'll know your power supply has a lot of leads coming off it. You connect to a motherboard that operates on about 5.5 volts is what most of what's inside your computer runs on. I think. Things probably have moved on in the 20 years since I last built a computer. What does a relay do? Well, we have our low voltage supply, our low power supply, connected to the solenoid, which is this yellow disc here, this yellow cylinder, should I say, here. And right now you can see at these terminals, the left ones are connected, the right ones are not. That's fine. If a current passes through the solenoid, it attracts the soft iron armature, which is going to push this connection. So now the left two aren't connected and the right two are. So you can have a relay where when there's a current through the low power side, it allows a current through the high power side, or you can have it so it doesn't allow it. It's up to you. And that's a very simple relay. No current passes from the low power side to the high power side. The high power side is completely isolated from the low power side. That's the point of a relay. The last type of device is a charge-coupled, not charge-coupled, RCD, residual current device. There we are, it's written right in front of me. Now with the residual current device, this is a component which takes the place of a fuse. Unlike a fuse, where inside the fuse, when there's too much current, a wire melts and you've got to replace the fuse. With this one, if there's too much current, the force, the magnetic force on the iron armature becomes so strong that it can pull the iron armature, disconnecting the circuit. So the current under normal operation, and I'm not sure where it comes in and goes out on this particular relay because there's a lot going on here, but the current comes into the relay, passes through the coil, then passes through the coil and then comes out again. And there's an iron armature. And if the iron armature moves, it actually breaks the circuit. But it also latches when that happens. So if the right amount of current is passing through the coil, so let's say it's a 13 amp RCD, so less than 13 amps passes through the coil, then the magnetic force on the armature isn't strong enough to pop it out. There's springs holding it in place. But if enough current passes through the coil, the force, so let's say I've now put 14 amps through my 13 amp RCD, more current, so stronger electromagnet. It's now stronger than the force of the springs holding the armature in place. So the armature pops out. And when the armature pops out, it's part of a switch that breaks the circuit. But it latches in place. So now, no current passes through the coil anymore. No current passes through anything anymore. It's been cut off by pulling that armature. However, oops, go forward again. However, we've got a switch that we can push that mechanically pushes the armature back in place. So that's how an RCD works. I might do a better video all about RCDs at some point because they are interesting. Yeah, that's all I need to say. In a circuit breaker, relay, electric bell, it's the same for all of these. Soft iron armature attracted to the electromagnet when current flows. If enough current flows. It's the same with them all. So let's move on to lesson 92. Lesson 92 is introducing you to the motor effect. So the motor effect is the effect where there is a magnetic force on a current-carrying wire that's in a magnetic field. So as I said, if there's a current-carrying wire, there's a magnetic field around it. Let's zoom in on this diagram on the top left. So here we've got the north pole of a permanent magnet on the bottom and the south pole of a permanent magnet on the top, and the rest of the permanent magnet is this curved bit of magnet around here, which I'm not that interested in, which is why I've just left it as white. The green arrows indicate the magnetic field from the permanent magnets. So that's what those green arrows are. The yellow arrows are the magnetic field that you get because of the current carrying wire carrying a current into the board. If you use your right-hand grip rule, you can see that the field lines go from left to right across the top. They go right, down at the right-hand side, up at the left-hand side, and so on. So the current's going in, the magnetic field is doing this. Exactly as we said, with the field lines closer together, nearer the wire, farther apart, further from the wire, further apart, farther from the wire. So that means that we have a weaker and weaker field the further we go from the wire. If there was no permanent magnet around this current carrying wire, the magnetic field would be the yellow arrows. If there was no current carrying wire, we had the permanent magnets, the magnetic field would be the green arrows. But we've got them both. So when we've got them both, on this side, the fields are both in the same direction, so we add them together. They're vectors, we add them together, they have a direction. On this side, they cancel out. But it's not a complete cancellation, because if you look over here, the downward arrows are closer together than the upward arrows. So in this region, the downward field is actually stronger than the upward field. But if we go far enough away, the yellow arrows are farther apart than the green arrows, so the upward field becomes stronger than the downward field. So if I were to very cleverly, very carefully, for every point in this space, calculate what the resultant magnetic field was, it would look something like this. This is just a doodle, but it would look something like this. We've got the cancellation here, we've got the field when it's closest to the wire doing that, and so on. Now you'll notice that these field lines are actually curved. Field lines don't want to be curved. That's not the most energetically favourable state. They like being as short as possible, straight lines or small circles, but these field lines continue into the permanent magnet. If I zoom out a tiny bit, there we go. We haven't drawn it as such, we haven't drawn the whole picture, but these field lines would go, each of these would go up through the magnet, round, down and back to there, because they all form closed loops. And you can see that where these field lines are really strongly curved, those closed loops are longer than they would be if those field lines were straight. So how does the universe rectify this problem of bent field lines? It tries to straighten them by pushing that wire to the right. Now that is a very naff way of visualizing and understanding what's going on, but it works and it will help you. Sometimes it's called the catapult force, the magnetic catapult force. That current carrying wire feels a force to the right in this magnetic field. Now, drawing a field diagram every time you want to work out what the direction of the force is going to be tedious, time-consuming, difficult. You don't need to. We can simply use Fleming's left-hand rule. And in an exam question, if you ever get a question, why is the force in this direction? The answer is Fleming's left-hand rule. Fleming's left-hand rule. You take your left hand, you can see a picture of it here. Each of our fingers and thumbs has a particular, or represents a particular quantity. The finger orientation is very important. It's not like this. It's like this, okay? Imagine that you are just pointing something out with your thumb extended and your finger extended, your index finger as far as they can, and then you just extend your middle finger just so that your thumb and your middle finger are 90 degrees to each other, your middle finger and your index finger are 90 degrees to each other, and your thumb and your index finger are 90 degrees to each other. So every one is 90 degrees to the other. That is how you want to arrange your hand. Then your thumb indicates the direction of the force, the magnetic force that the wire will have. B is the magnetic field direction. Actually, it's the magnetic flux density. You can calculate it. It's a quantity that is higher when the magnetic field is stronger. So magnetic flux density indicates how strong the magnetic field is. Magnetic field has a direction, so B indicates the direction of that. Why do we use a B? It's a very funny and long story. Blame James Clerk Maxwell. I'm not going to go into that now. But so it is a funny story, though. So B is the direction of the magnetic field in this picture. I is the direction of the current. Now, I've got a problem with this because current is a scalar. It doesn't actually have a direction. So I prefer to have I as the direction of the displacement of effective positive charge in our circuit. That works for me because displacement is a vector, but you'll never see that in textbooks, on videos, or anything else. It'll always say direction of current I. I have a real problem with that. It's not a vector, it's a pseudo-vector, but doesn't matter. We know what we mean when we talk about direction of current. We mean the direction that positive charge would effectively flow in a conductor. Yes, I know the electrons flow the other way. It doesn't matter. Yes, I know the electrons are flowing in the opposite direction to I. It doesn't matter. It's effective flow of positive charge. We talked about this in video 4. Apologies. So you can use those three fingers, those 2 fingers and a thumb, those 3 fingers. Let's take it in the bottom example here. If we ensure that our middle finger is pointing into the board, into the screen, because that is what the X indicates, is a current going towards the screen, into the screen. The magnetic field it's in, so we ignore the magnetic field of the current, caused by the current, and just look at the permanent magnetic field the current carrying wire has been placed in. That's the green one. That's up. So our index finger is going to be pointing up. Middle finger into the screen, index finger up, thumb is pointing to the right. So the magnetic force on this wire is to the right. So that's how you use Fleming's left-hand rule. I mean, let's look at this example here. We've got a north pole in front, south pole behind. So the magnetic field, that's the index finger, is pointing into the board. The current is going to be flowing from positive to negative. So that's flowing from left to right. So that's that direction. So I have to do it this way around. So that's that direction. So the force is up, the direction of the thumb. You just have to know that. Now, if I had to take 2 wires and I were to pass a current in different directions through those 2 wires in that magnetic field, then they'll feel forces in opposite directions. If instead of having just 2 wires doing this, I connected it to make a loop, well, in a loop, the current's travelling in opposite directions in each side of the loop. That's how loops work. Bit of wire going towards you, turns round, then goes away from you. So if we had a loop, we would have forces trying to twist that loop around. And if we allow those forces to accelerate that loop around, then because of momentum, it's going to carry on past that point, but then it's going to oscillate and then just sit and sit with the loop of wire orientated so that the plane, in this picture, the plane of the loop is vertical. So what we really want is a way of switching the direction of the current in the loop. So as we rotate this coil around, we switch the direction of the current to keep it rotating. Then we switch it again to keep it rotating. Then we switch it again to keep it rotating. Now, I usually demonstrate this with actual motor kits, or I'll get simulations out to show it. But again, this is just a summary. Get some notes out there, so I'm not going to do that now. How do we switch the current? Well, not only that, how do we make sure that as this coil, this loop of wire spins around, it doesn't just twist up all the wires that are connecting it to the rest of the circuit, to the power supply? We use what's called a commutator. A commutator connects two parts of the circuit through a part that is able to move, to slide, so that we can have moving parts still in electrical contact. It involves having things like carbon brushes, like you've got here, connected to copper rings or brass rings. And so there's an electrical connection that is maintained as this coil in the middle is rotated around. If we take our commutator and we split it, then we are able to change the direction of the current through the coils every half a turn of those coils. So now we have a way of maintaining electrical connections, but also switching the direction of the current. So we can get continuous rotation of coils by using a split ring commutator. Yeah, you do need to know that. It's complicated, but you do need to know that. This equation down here is the equation to calculate the magnetic force. Yes, it's physics. You're not going to get away with just using Fleming's left-hand rule and vague arm-waving arguments. We can calculate the force, the magnetic force, in newtons by using this equation. B is the flux density in units called Tesla. Remember, that is a quantity that indicates how strong the magnetic field is in that region. At least it gives us some idea. I is the current, same as it ever was. L is the length of wire that is exposed to this magnetic field. So the length of wire that is in the magnetic field. So how can I make a magnetic force bigger? Have more wire in the magnetic field. That's why we have more turns on our coil in a motor. How can I make I bigger? How can I make F bigger? Make the current bigger. Make I bigger. So high current motors are going to spin faster, we would hope. Well, it depends. How do we make the F bigger? We use stronger magnets. When we look at things like the Large Hadron Collider, where we're trying to pull charged particles round in a big circle, we need huge forces acting on those particles, so we use very strong magnets to do that. Okay, that's the end of the motor effect. Let's look at the generator effect. The generator effect, so this is lesson 93. So the generator effect, this is an interesting idea. If we've discovered that currents have magnetic fields, so does that mean that magnetic fields can cause currents? Well, sort of, yes, but you're not just going to get a current, which, remember, is involved in the transfer of energy, unless you've got some way of doing work on your, well, generator, your electromagnetic machine, unless you have some way of doing work. So you have to have some sort of changing magnetic field relative to the coil of wire, relative to the conductor, for there to be a current induced in that conductor. And actually, the current isn't what's induced. It's a potential difference across the conductor which is induced. And if the conductor is part of a circuit, then that will cause there to be a current. So this is, I think, the most complicated topic of the GCSE in physics. I really do think the generator effect is the hardest part. So let's define some words. We've got polarity. That which end of the solenoid is north, which end is south. Which pole is which? We call that the polarity. We've got the generator effect. That's the idea that if there's a change in magnetic field near a conductor, or through a conductor, I should say, then the conductor will have a potential difference induced across it. And so that if there's a complete circuit with that conductor in, then a current will flow through that circuit. That is the generator effect. Electromagnetic induction is the idea that a potential difference is induced across a conductor when there's a changing magnetic field through the conductor. We call that electromagnetic induction. You can have a changing magnetic field by either having a magnet that's moving or a magnet that's changing in strength, or having the conductor itself moving. Either of those will do the job. Induced polarity of a solenoid. So this is, we are inducing a magnetic field in the solenoid. Why is that? We're inducing a magnetic field in the solenoid because we have a current in the solenoid. Why do we have a current in the solenoid? Because there's a potential difference across the solenoid. Why do we have a potential difference across the solenoid? Because the solenoid has a changing magnetic field passing through it. Why does a solenoid have a changing magnetic field passing through it? I'm looking at the diagram on the bottom right here. It's because there is a magnet moving relative to that solenoid. So there is a induced polarity of that solenoid, and that polarity will always be in such a way that it opposes that changing magnetic field. If the south pole of the magnet is moving towards the solenoid, which is what's happening now, not now, but it was happening. I'll say now again in a second. South pole moving towards the solenoid now. Then what's going to happen is the solenoid is going to have a potential difference induced with, if it's a complete circuit, with a current that is going to have a magnetic field through that of that solenoid, an induced magnetic field, such that the left-hand side becomes a south pole. If I push a south pole towards the coil side closest to that south pole becomes a south pole. Why is that? Because then there's a force that's pushing against me. So I'm now having to do work to push that magnet in. Why am I having to do work? Because I'm causing there to be a current, and currents cause energy to be transferred into thermal energy stores of the wires. Or if this is a generator, it could be connected to a light bulb or something. What if it's not a complete circuit? Well, there's no current. So I can just push that magnet in and out with no force opposing me. But as soon as I connect this solenoid in such a way that there is a current, there isn't in this picture, it's connected to a voltmeter. Voltmeters have infinite resistance, or near enough, so there's no current that flows through them. But if instead of a voltmeter I had a lamp in this picture on the bottom right, then as I push the magnet in, the solenoid is going to have a south pole induced on the side closest to the right as I push the magnet in, and the left as I push the magnet in, to oppose that motion. If I pull the magnet out of the left-hand side, then the left-hand side of the solenoid has a north pole induced to attract the magnet back. So whether I'm pushing the magnet in the left-hand side or pulling it out of the left-hand side, the coil is going to have a magnetic field induced with a induced polarity that causes me to have to push or pull, to exert a force on that magnet so that I'm doing work. And we could do all the same thing for the right-hand side, looking at the North Pole. If the North Pole approaches the right-hand side, then we have an induced polarity of north on the right-hand side of the coil. If the North Pole on the right-hand side is moving away from the right-hand side of the coil, then we'll have a South Pole induced on the right-hand side of the coil. And it's all about opposing that change. The coil does not like the changing magnetic field. And if it's a complete circuit, then poles are induced. If it's not a complete circuit, poles aren't induced, but we do have induced potential difference across the coil. It just can't make a current without a complete circuit. So that's induced polarity. The North Pole approaches, this is what I've just explained. In fact, those bottom two boxes are what I've just explained. Solenoid, just a reminder, is a coil of wire. Bit on the top here, I've explained in words already. It's just the same thing again. Here's a picture showing how you can figure out the direction of the magnetic field if you know the current. You can also work out the direction of the current if you know the magnetic field. You could actually use the thumb for the direction of the magnetic field as well. If you look at this diagram here, if the thumb is pointing the direction of the magnetic field through the solenoid, the fingers indicate the direction of the current that causes that magnetic field, the current in the solenoid. So the right-hand grip rule, very powerful. You can use it for thumb is current, fingers are field, magnetic field, or you could use it for thumb is magnetic field, fingers are current for a solenoid. But don't get it confused with the left-hand rule for motors. Okay, don't get the two confused. Right-hand grip rule, relationship between current and magnetic field, left-hand rule, Fleming's left-hand rule, motor effect. Nothing to do with motors, this is generators. If I just sat this magnet here and didn't move it, there'd be no changing magnetic field, therefore there's no potential difference induced. So we have to have a changing magnetic field in order for us to have an induced magnetic field in the coil, in order for there to be an induced potential across the coil. Really difficult topic, really difficult, but the idea of changing magnetic fields is absolutely key. Let's have a look at this in practice then. Lesson 94, the alternating current generator. So here we've got a whole bunch of animations to excite the senses and bamboozle people, but here we go. Let's first of all use the definitions here. Now these are the way AQA defines these. I don't think this is universally agreed upon. They define an alternator as being an alternating current generator and a dynamo as being a direct current generator. That being said, an alternator, a dynamo, like you might have on an old bicycle to power your bike lights, is actually an alternating current generator. So I'm not sure how much I agree with this definition of alternator and dynamo, but this is what we are using, so let's stick with it. In the top example, we have a coil of wire being made to rotate in a magnetic field. So I am pushing this wire around. I'm doing work. I'm just going to close this a minute because I've got the sun in my eyes. As I push that coil around doing work, the coil sees a changing magnetic field. When the coil has a plane that's vertical, loads of fields going through it. When the coil has a plane that is horizontal, no field goes through it. It all misses it. So we have a changing field as seen. We actually call it flux, but don't worry about that. A changing field as seen by the coil as the coil rotates. Well, if the coil has a changing magnetic flux density, then there is a current induced in the coil. Well, a potential difference induced across the coil, which if the coil is part of a circuit means a current will pass through the coil. And if a current is passing through the coil, it has its own magnetic field opposing that change, which means that we have to do work to get this thing to spin around. So that is a simple example of an alternator as defined by AQA, because the potential difference keeps changing direction. Why is that? Well, I should say the potential difference keeps changing polarity, because potential difference is a scalar anyway. Why is that? Because the field is going from north to south, from left to right, which means as the coil rotates, the direction through the coil of the field keeps changing. And it also changes whether it's increasing or decreasing. So that changes the polarity of the induced potential in the coil, which is what this all says up here. What we could do is we could connect this to a circuit by using another type of commutator called a slip ring commutator. Here, we don't have a split. We just have two brass rings connected to our carbon brushes. And so if we pull this thing around, mechanically pull this coil around, make it move by pushing it, and we have something connected to the other terminals of these commutators here, so this terminal at the top and this terminal at the bottom, then there's a constant electrical connection with the coil. So we've now got a continuous generation of AC. It's an alternator. We could use a split ring system and make a DC generator, a dynamo. We could do that, and that would be fine. But this picture just has the slip ring for an AC generator, an alternator as defined by AQA. Rather than moving the coil relative to the magnets, we could move the magnets relative to the coils, which is the example on the bottom. It's exactly the same physics though. So if you look at the coils, they at one point have very little field passing through them. At one point there's zero. And at one point there's lots of field passing through the coils. If you look, you can see the green lines are bunched together at the poles. That's our definition of poles, where the field lines are strongest. And so it goes red, blue, Blue, if the red is the north pole, then when the red is pointing towards the coil on the left, there's a lot of fields pointing from right to left through that coil. When the blue, which is the south pole, is pointing towards the coil on the left, then there's a lot of fields going from left to right towards the south pole. And in between, there's no field passing through the coil at all. So the coil sees a field constantly changing. Just like in the top example, the coil feels a field constantly changing. But the reason is, on the top example, the coil is rotating. On the bottom example, the magnet is rotating. They do produce different waveforms of AC, but they're both AC, so they're both examples of alternators. You can take an alternator, you can take an alternating current and make it a direct current by using diodes as rectifiers. We looked at diodes in the electricity video, either video 4 or video 5, I forget. So how do I make a generator better then? How do I generate more current? Well, I would need more turns on my coil. I would need to increase the frequency that the coil rotates, because if it's moving faster, the rate of change of flux linkage, that's what we call it, the rate of change of magnetic field passing through the coil, is higher. The higher the rate of change of magnetic field passing through the coil, the greater the induced potential difference, and therefore the greater that the current that the generator will generate will be. So induce the frequency of the coil. Induce the maximum area. If it's a bigger area, then it's going to be cutting through more of those field lines, and so our change in flux over a time period is going to be greater. Increase the strength of the magnets. Makes the field stronger, so bigger variation of field if you've got stronger magnets. And then just as before, soft iron. Soft iron reinforces those magnetic fields, making the magnet stronger. So that's what you can do to increase the peak induced potential difference. It says voltage here. Voltage means potential difference, but we prefer to call it potential difference rather than voltage. What about a microphone? Well, a microphone is a generator as well, except unlike these where we're rotating our coils, here the coil just shifts backwards and forwards through a magnetic field which is produced by a permanent magnet. And the coil is attached to a diaphragm, a very lightweight card or paper diaphragm. And so there's sound, just like what happens with the tympanic membrane in your ear, where that vibrates backwards and forwards. This card membrane will vibrate backwards and forwards. That will cause the coil to vibrate in and out of the magnetic field, which will induce a current, and we can stick that in an amplifier and increase that signal. So that is how a microphone works. I don't think it's too complicated. When a plane of a coil is perpendicular to the flux density, no potential is induced because no field lines are being cut as the coil rotates. The sides of the coil move parallel to the flux density. It's complicated stuff. You don't really need that stuff. Perpendicular to the flux. Yeah, when the plane is perpendicular to the flux. So if you look at this diagram on the right, that is now, and those times, there's actually no potential difference induced. It's also when if you're looking at the AC waveform, it's when the potential is switching polarity. Right, okay, that is complicated stuff. It gets no easier. Lesson 95 on transformers. So we've met the idea of transformers earlier on in video 5 when we talked about their role in the national grid. And we learned back then that transformers change potential difference. They need alternating potential difference, but that doesn't matter. They change the potential difference. They can step up the potential difference, increasing it, or they can step down the potential difference, decreasing it. And we learned that we need transformers at the beginning of the national grid to increase the potential difference, to reduce the current through the wires, to cause less of a heating effect in the wires, so we get higher efficiency energy transfer to our home. And then in our home, we need to before our home, we need to step down to increase the current again and decrease the potential difference to safe levels. But how does a transformer work? Well, it works a bit like this. Now, in A level, we go into real detail about how a transformer works, and it is complicated. We have two sides to the transformer, the primary side and the secondary side. Think of the primary side as connected to the source of the energy, where the energy is coming from, and the secondary side as being where the energy is flowing out of this transformer. Think about it that way. So we have an alternating potential difference. Now, this is labelled here as plus and minus, and at this instant in time, that may well be plus and minus. But this is alternating, which means it's going to keep switching the direction of that plus and minus. What we would usually have is a live connection and a neutral connection. All right, okay, you remember that from video 5 as well. So we'd usually have a live and a neutral. The live would be switching between positive and negative, and the neutral would be fixed at 0 volts. And then we'd have a live and neutral on the secondary side. Maybe the one labelled plus is a live and the one labelled minus is a neutral. So this diagram's not great. When there is current passing through the primary coil has a magnetic field because that's what solenoids do. So why have we got a current passing through the primary coil? Because there's a potential difference across the primary coil. Now, the potential difference across the primary coil keeps changing direction. It's alternating, which means the current through the primary coil keeps changing direction, which means the magnetic field that the primary coil has keeps changing direction. The core of the transformer is made out of soft iron. The soft iron core becomes magnetized and therefore strengthens the magnetic field around it. So the magnetic field follows the core around in this shape. In real transformers, we wouldn't do them this shape. We'd actually make them a sort of figure 8 shape and put the windings, the wires, all around the middle bit. This is fine for a school demonstration, though. Now, there's no electrical connection between the wires on the primary side and the wires on the secondary side. No connection at all. The magnetic field around the core is changing. The secondary coil, therefore, has a changing magnetic field passing through it, changing in strength, but also changing in direction. And so there will be an induced potential difference across the secondary side. We've already talked about that in the previous part of this video. Now, it turns out, if I have more turns on my primary side than my secondary side, then I am stepping down my potential difference. If I have more turns on the secondary side than the primary side, that's not what's shown here, then if I have more on my secondary, then I'm going to be stepping up my potential difference. Now, why is that? We will talk about in A level. That is quite complicated. Just know that that is the case. This is an exciting hint of what's going to come up later on in your physics education. There's a bit down here where we said how it works, alternating current, blah, blah, blah. It's just what I've explained. Bit here about how to make it more efficient. Put windings. I mean, this is an example. This is a figure of 8 core, and the windings are around the middle bit. So we might have primary here, secondary here. Actually, this is a microwave oven transformer, so it's even more complicated. There's a third set of windings, and the core itself is connected somehow, so don't worry too much about that. Don't mess around with microwave oven transformers. They are lethal. Really, truly lethal. What else can we do? Well, they've got a conductor. It's an iron core. It's a conductor, and it sees a changing magnetic field. So the core itself will have currents induced in it, and those currents will be swirling around in the core. Not swirling around like this, swirling around this bit here, swirling around this bit here, swirling around this bit here, swirling around this bit here. Whenever you've got a current swirling around, that means that there is work being done by that current, which means we're transferring energy into the thermal energy store of the core, which is going to make this less efficient. So what we want to do is reduce those currents. We call those eddy currents, and we reduce those eddy currents by laminating the core. So we take a square with a cut in the middle. So we take a square of of iron, and then we take another one, and another one, and another one, and we just glue them together with an insulating glue. If we look here, you can possibly see, yes, you can just about make out there are lines here, and there are lines here. These are plates, figure-of-8 plates that are now bolted together with an insulator between them. So that is a laminated core, which makes the core much more efficient because it reduces those eddy currents. Iron magnetizes more easily than steel, so we call it soft. We've already talked about that. I think we've covered this one. So we're now going to move to the last lesson of the topic of transformers. Lesson 96 is using transformers. Transformers in action. So I said on the national grid, we step up the potential difference, the average potential difference, between the power station and the national grid, the cables. Then we step down between the national grid and us, the secondary consumer. That's us, that's the home. This is the US power grid, so 240 and 120 volts rather than 230 volts, which is what we say. But there's a transformer to step down again. So that's what we looked at in our previous lesson. What was it? Video 5 about the national, where the national grid came up. Okay, red section is the generation section, blue is the transmission, green is the distribution of our energy into the customers, which is the black part there. So we need to be able to calculate how much our potential difference changes because of a transformer. And remember, it had to do with the number of turns. And it turns out that the ratio of the potential difference across the primary and secondary coils is equal to the ratio of turns on the primary and secondary coils. Don't say N is the number of coils. There's one coil, but it's got a different number of turns on it. So if we look at the previous example, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think that's 15 turns and 1, 2, 3, 4, 5, 6 turns. I think this is 15 turns on the primary, 6 on the secondary. 15 on the primary, 6 on the secondary. So if I do 15 on the primary divided by 6 on the secondary, that means that the primary is 2.5 times higher than the secondary. That's what it is. VP over VS equals 2.5. So if the secondary is 10 volts, then the primary is 25 volts. We're just using this equation. Why do we use a step-up transformer at this stage in generation? Because, as we said before, we want to reduce the current in the transmission lines. And we do that by increasing the potential difference. Why is that? Because for a transformer, if we assume it's a 100% efficient transformer, which they're actually pretty high efficiency, so it's not a terrible thing to say, the power into the transformer, that's the potential difference across the primary side multiplied by the current passing through that primary winding, is going to be equal to the power coming out the other end. That's the potential difference across the secondary coil multiplied by the current passing through those secondary coil, the secondary windings. So that is power equals potential difference times current. And if we say the same power, so the same amount of energy per second is going into the transformer as coming out, because it's 100% efficient, and I mean coming out electrically, if you know what I mean, being transmitted to the transmission lines, not just heating up the transformer, then we can say that if I double V, so VP is half of VS, VS is double VP, then IS has to be half of IP. If VS is 3 times VP, IS has to be a third of IP to make this equation work. That's how numbers work. In a lesson, we'd go through some examples, but again, just a summary. Why are we doing that? Because in the transmission lines, we want I to be as small as possible, so the power wasted in the national grid by the transmission lines is as low as possible. We can make the resistance low in the cables, but there's only so far that'll take us. We have a bigger impact on our wasted power by decreasing, a bigger positive impact by decreasing the current, because the current is squared in this equation. And we derived this equation back in video 5 as well. I think I've covered everything here. Why do we have a step-down transformer at all on the consumer side? Well, because if I had hundreds of thousands of volts between connections on my home, my electrical terminal, I'd get sparks across them. It'd be very, very dangerous. So 230 volts, you're going to get less than a millimeter of a spark when you unplug it, much less than a millimeter. So it's safe. It's safe. I think I've covered everything we need to know about this now. Just practice using these equations. Again, you can use Isaac Physics to do exactly that. I would thoroughly recommend you use the Isaac Physics resources to practice all this sort of stuff. So concludes the penultimate video. The last video on space is coming up soon. Hope you found that useful. Remember, I've been reminding at the end of every video, weekly tuition sessions, live, interactive. Interested? QR code. Go to website. Sign up. Very, very cheap. Free if you can't afford it. Just let me know. And then you can take part in interactive tuition sessions. You ask questions, I answer. I ask questions, you answer. Everyone benefits. Video ends. Bye-bye.